hope you had a great holiday. It was nice to be away for about a month. Please raise your hand if you're new to this section but didn't take my 564 last quarter. Okay, good. So this is going to be a lot of fun. This is kind of the quarter that I've been looking forward to the most, where we get to talk about really useful applied math, dealing with partial differential equations, data analysis, all kinds of cool stuff that we kind of built up the tools to study in the last quarter. Okay? So the basic organization of the class is roughly the same as before. The video lectures will be online. There's a Catalyst discussion board. There's a midterm and a final exam. Slightly different than last quarter. These are each going to be equally weighted at 20% of the grade. So it's really a midterm 1 and a midterm 2. After looking at some of the comments for the course last quarter, one of the consistent comments was that a little bit more homework and a little bit more in-depth homework would have been helpful. And so I'm having, I know some of you are wondering who would possibly write that. So I'm going to have a little bit more homework and a little bit more in-depth, but not much. Okay? So instead of 5 homeworks, we're going to have 6. Each of them are worth 10% of your grade, so homework's total of 60%. The first one's going to be due 2 weeks from now on Friday. Okay? Same deal with the midterm and the final. They're take-home, cumulative. You can treat them like a qualifying exam. The teaching assistants are Robert and Humin. Are you guys in the class? Can you raise your hand? Okay, so Humin's at the back. I guess Robert's not here right now. Their office hours will be decided soon. My office hours are going to stay the same. Did those work? Sorry, is there anyone that those did not work for? Okay, if anyone wants to make separate office hours with me by appointment, feel free to do that. Let me know. I can always create a second office hours at a time that's better for other people. Okay, so the syllabus. So last quarter, I had a rough idea of what I wanted to teach you. This quarter, I have a slightly better idea of what I want to teach you. So I have an empty syllabus here broken into 3 basic parts. Okay? So part 1, for the first 2 weeks, we're going to be talking about complex analysis. And if I remember, most of you have not taken a course in complex variables before. If any of you have, would you raise your hand? Okay, so just a couple. So this will be new and interesting for most of you, and it'll also be pretty aggressive and pretty fast-paced. Okay, so this is going to be important. Complex analysis is super important for partial differential equations and analysis. But it's going to be kind of a trick fitting in the stuff that I think is really important without telling you too much or too little in 2 weeks. The main meat of the course is in part 2, which is partial differential equations and transform methods. So this will be about 5 weeks in the middle. We're going to talk about Laplace transforms, Fourier transforms, and how to solve partial differential equations every way that I can think of to tell you in 5 weeks. Okay? Most of you have seen some PDEs before, but we're going to go more into depth and really get to the bottom of a lot of cool math. And this is, part 3 is where I'm deviating from how this course has been taught in the past. This is my attempt to make this course more modern and relevant for your research today. Most of the time, courses teach you about the analytic by-hand solutions to PDEs, which are very useful, very important. But I really want you to know how to solve PDEs on a computer, or at least have the basic understanding of where you would go to look if you needed to solve PDEs on a computer. Okay, so there's a lot of great classes around campus, like AMath 581, 582, that go much more into depth in part 3. And this is going to be kind of a teaser to get you primed for that material in case you want to go farther into data analysis and numerics. Okay, and these methods in data analysis are very relevant for partial differential equations, but they're also relevant for everything else you're going to do in research. Anytime you have a data set, you're going to be able to use these methods. Okay? Any questions about the organization or syllabus or anything? Okay, good. Okay, that's it for the computer. Okay, so since you all know me and we don't have to do the long introduction, I'm going to jump right into complex analysis. I should probably tell you when I'm traveling this year, and I'll do that next lecture. Okay, so I'm going to be gone maybe 3 out of the 30 lectures, but I'm going to pre-record them and post them online so that you can watch the videos. Okay? Okay, so complex numbers are not too complicated. We've already looked at this a little bit, but I'm just going to go into a kind of a review. So we always call I an imaginary number, and we call the numbers we're used to, like pi and 5, real numbers. But real numbers are not really complete without imaginary numbers. Okay, so we need complex numbers. And we need complex numbers so that our mathematical operations like squaring numbers and having roots of polynomials are complete. Okay, so we need these numbers for solutions to polynomials. Right? It's really weird that we have this entire branch of math called algebra, but it's not complete if you don't have complex numbers. So for example, if you have x squared plus 1 equals 0, then we have x squared equals minus 1, and x equals square root of minus 1. And unless we invent some new number, we're stuck. Right? There's no real number that's the square root of negative 1. So we define I equals the square root of negative 1. Okay, this is not new to any of you. All of you know about I and square root of negative 1 and complex numbers. It turns out that these complex numbers, I, are extremely important in differential equations. Okay, partial differential equations and ordinary differential equations. So remember when we had the spring on a mass? Sorry, maybe it's a mass on a spring. And you let this system go, it oscillates and damps out. And the oscillations came because the eigenvalues of our ODE had a complex eigenvalue, not just a real eigenvalue. You have similar phenomena in PDEs, and basically, whenever we see oscillations in the real world, there is some kind of phase component or some imaginary component to some eigenvalue of some problem. Okay? So any complex number, and we're going to call these complex numbers z. So x and y are real numbers. Z is a complex number. So we can write any complex number z as a sum of real and imaginary parts. Okay, so z equals x plus I, y. Okay. And so this defines a two-dimensional plane or a coordinate system where we can write any number, any complex number. So we define the complex plane using this script bold C. And you have your real axis as the x-axis and your imaginary part as the y-axis. And any number z is just a sum of some x plus I, y. Okay? Now, in the last quarter, we also saw that there's a very convenient polar coordinate representation for these complex numbers, where our complex number has some radius and some angle phi. Okay? And so this is going to be a very, very useful alternative representation where we can write x equals r cosine theta, y equals r sine theta, And you have this basic relationship that z equals some radius r times the complex exponential of I theta. And this is probably the most important formula that I'm going to teach you in complex analysis. Everything comes back, like anytime you're dealing with complex variables, chances are it's a good idea to think about them in these polar coordinates r e to the I theta. This is going to be very useful to go back to this form, where e to the I theta is equal to cos theta plus I sine theta. Okay, this is called Eulers' formula. E to the I theta equals cos theta plus I sine theta. If it has Euler's name on it, it's really important. And this is the x part and the y part. And you could get this Euler's formula by Taylor expanding this exponential function and plugging in I theta. Okay, and you get a real part, which is cos, and an imaginary part, which is sine. Okay, this is basically review. I'm going to go a little bit slow today and just go over the basics of complex numbers and addition and multiplication and give you some examples of functions that you're familiar with that we can write as functions of a complex variable. But then very quickly we're going to be doing things like taking the derivatives of these functions and integrating these functions and getting into some really interesting math. So this is going to be a little bit slow, but bear with me, okay? So you can have addition and subtraction. And addition and subtraction of complex numbers is exactly the same as in real numbers. So you have z1 plus or minus z2. You just add the real part of z1 plus z2, and that's the new real part. And you add the imaginary part of z1 and z2, and that's the new imaginary part. So that equals x1 plus x2 plus I times y1 plus y2. Same for subtraction. Okay. Multiplication is pretty simple. So if I have z1 times z2, I can just take the real plus imaginary form and multiply them out like you would a polynomial. Okay, so I'm going to multiply all four of these pairs. And anytime I see an I times I get a negative 1. Right? Pretty straightforward. So x1 times x2. And then the other real part is the I squared times y1, y2, which is a minus y1, y2. And then my cross terms both have an I on them. So plus I times x1, y2 plus x2, y1. Does that make sense? Right? You just multiply this out, collect all of the real parts on one side, all of the imaginary parts on the other. That's basically the name of the game, is keep the real parts and the imaginary parts separate. Okay? Division is a little bit more complicated, but not much. So if I have z1 divided by z2, then I'm going to do the same thing. I'm going to take x1 plus iy1 divided by x2 plus iy2. Now, how many of you remember how to get rid of a complex number in the denominator? Multiply top and bottom by the complex conjugate. So there's a rule. So z bar is the complex conjugate, and that's equal to x minus iy. So instead of if z equals x plus iy, then z bar equals x minus iy. That's the complex conjugate, really, really important. And it's true that z times z bar is always real. Okay, you can just multiply these out and figure out for yourself that the cross terms with an I cancel, and you're left with x squared plus y squared, which is the length of z. Okay, squared. So we're going to multiply this top and bottom by z2 conjugate. and we get z1 times z2 bar divided by the length of z2 squared. Okay. This multiplication is just the same as this formula up here, and this is a real number, the length of z2 squared, r squared if you like. Okay. All of this is easier in polar coordinates. So for example, z1 times z2 in polar coordinates is just r1, r2, e to the I theta 1, e to the I theta 2, which is r1, r2, e to the I theta 1 plus theta 2. Much simpler to do multiplication in polar coordinates. You multiply the radii and you add the angles. And the same thing with division. z1 divided by z2 is just r1 over r2, e to the I theta 1 minus theta 2. Much, much, much simpler in polar coordinates. And I'm going to draw a picture because I like these pictures a lot better than algebra. Okay, so let's see. So let's say that I have two vectors. I have z1 and z2. And they have angles theta 1 and theta 2, and radii r1 and r2 like above. So the product of these, I just take this radius times this radius, the lengths multiply, and I add up theta 1 plus theta 2. So I get something that is theta 1 plus theta 2 with a radius that's r1 times r2. And that's the product z1 times z2. Okay, so there's a very nice geometric interpretation of matrix complex number multiplication. You just multiply their radii, add their angles. Okay? All right, good. So now, are there any questions before I get into complex functions? Nope. Okay. So now I want to tell you about functions of a complex variable. I've already shown you one function, the complex conjugate, and I guess e to the I theta is also a function of a complex variable. But almost every function you can think of can be written as a function of z instead of just a function of a real x. And this is going to be a really important concept. Okay, so we have functions of z. And what we're going to find out towards the end of the lecture today and in Wednesday's lecture, is that simple functions that we're used to of real numbers might become really weird or nasty when we give them complex variable arguments. Okay, so there's lots of funny, weird things that can happen in the complex plane that don't happen for real numbers. Okay? So I'm just going to go down the list. So functions that you're used to that you can also write down in complex plane are things like powers of z, right? Polynomials. You can write down polynomials in a complex variable. So this would be something like r cos theta plus I sine theta taken to the power n, right? Which is r to the n cos theta plus I sine theta to the power n. So this is a power function. You can have polynomials. So I can have the sum from k equals 0 to n of some number times z to the k. This number could be a complex number. This could be square root of -1 times z to the k. Okay? So I can have complex polynomials built out of these complex monomials. I can have complex rational functions. So I can have a ratio of two polynomials. Okay, so I can have a polynomial divided by a polynomial, a rational function. We're used to those in real numbers. Same thing in complex numbers, except these can get really, really strange in the complex plane. I can also have things like Taylor series. So these are finite polynomials, right? But I could have a sum k equals 0 to infinity of ak z minus z naught to the power k. I could have a Taylor series. And you have the same basic concerns with complex value Taylor series that you do with real value Taylor series. Like, does this converge? Is it actually defined? Can I take its derivative? Is it smooth? Things like that. So you can have Taylor series. And the Taylor series is only convergent if it passes the ratio test. Okay? So if L equals the limit as k goes to infinity of ak plus 1 divided by ak exists. And when I say exists, I mean this L is a finite number. It's not infinity. 5 or 10 or 0.1 or 0. Okay, so if this limit of one larger coefficient divided by the previous coefficient as k goes to infinity, if that limit exists, then this Taylor series passes the ratio test and it converges, and it has a radius of convergence given by 1 over L. Okay? So not all series that you can write down, not all numbers a, k will give you a convergent Taylor series, but they will converge, and it will be a nice, well-defined function if this ratio test exists. And then you'll have this radius of convergence. So these are some examples of functions that we're used to seeing. I'll write down some other functions in a minute, like e to the z and sine of z and cosine of z. But maybe I'll just give you an example of this ratio test first. So this is something you've all done in calculus, right? Ratio tests to see if Taylor series converge. So let's see if this exponential function has a convergent Taylor series. Okay, so e to the z is defined as the sum from k equals 0 to infinity of 1 over k factorial times z to the power k. Right? This is just the definition of exponential, and instead of plugging in a real number x, I'm plugging in a complex number z. And if you plugged in I theta, for example, and expanded this out, you'd get cos theta plus I sine theta. The odd terms would be imaginary, and the even terms would be real. Okay, so let's check convergence. Okay, so let's do this limit. L is the limit as k goes to infinity of, what are the coefficients that I'm taking? What's ak plus 1? 1 over k plus 1 factorial. And what's ak? 1 over k factorial. So this is ak plus 1, and this is 1 over ak. And so that's the limit of, right, all of these k factorials cancel out, and I'm just left with 1 over k plus 1. And in the limit as k goes to infinity, this equals 0. So L equals 0, and my radius of convergence is infinite, right? 1 over L. So this is the kind of thing that we're used to from regular calculus, and it still holds for functions of a complex variable. We still want to have Taylor series. We still want to be able to take derivatives. We still want to be able to write things as convergent power series expansions. Okay. Now, knowing e to the z equals this convergent power series, and knowing Eulers' formula, which is e to the I theta equals cos theta plus I sine theta, we can revisit our power z to the n, and we can actually find a nice simplified expression for this. I don't like this cos plus I sine theta to the power n, because if I wanted to evaluate this for a large n, I'd have to do a huge binomial expansion. Right? I would get like cos to the n plus n cos to the n minus 1 sine plus some other horrible mess. Right? It would be this nasty, nasty thing. But using Euler's formula, you can simplify this dramatically. So if I have z to the n equals r e to the I theta to the nth power, this equals r to the n times e to the I n theta. Right? If I take e to the I theta and I multiply it by itself n times, that's I theta plus I theta plus I theta n times, gives me e to the I n theta. Okay? And that equals r to the power n times cos n theta plus I sine n theta. Now, this is a really simple formula. This is exactly what this nasty expression equals. Okay? So if you expanded all this out, you get a bunch of stuff magically factoring into these two very simple expressions, cos n theta plus I sine n theta. It's a simple formula, but it's one of my favorites because it so illustrates why you want to be working in polar coordinates. And this is called de Moivre's formula. Not quite as important as Euler, but still important. And you can draw the same picture here. This is just like the picture for complex number multiplication, where in the complex plane, if I have z given by r and theta, then z squared is going to be given by r squared and 2 theta, and z cubed is going to be given by r cubed and 3 theta, and so on and so forth. Okay, so taking a power of a complex number is really simple. You just take its radius to that power, and then you take that power times its angle. Okay, n times its angle. Okay, any questions about this complex geometry or the Convergent Taylor series? We're going to be extremely interested in functions that have convergent Taylor series. We're going to give those functions a special name. We're going to call them analytic functions. And those are going to be the functions where we can do basic calculus. We can do derivatives and integrals and all of the things we're used to from calculus for functions that have these convergent Taylor series. And that's all I'm going to talk about on Wednesday and Friday, is how to take and do calculus on special functions that have convergent Taylor series. Okay? Okay, but that's for Wednesday and Friday. So I'm going to keep telling you about more functions. How many of you have worked with hyperbolic functions before? Okay, so I was a math major before I started doing engineering in grad school. And so this equivalent course in my grad school was the first time I had ever seen a hyperbolic function in real life. But they turn out to be pretty useful. So you have hyperbolic functions. And the great thing about hyperbolic functions, and actually trigonometric functions for that matter, is that they actually make a lot more sense in the complex plane. So there's a lot of things that you can do with hyperbolic functions that only make sense when you think about them in terms of complex numbers. So we're going to say sine h of z, or sinh of z, is e to the z minus e to the minus z divided by 2. I'm just defining this. We call this sinh, like it's easy, it's a sinh. Cosh of z, the hyperbolic cosine of z, is e to the z plus e to the minus z divided by 2. Any other meanings for the word cosh? Anyone knows? Oh, come on. Some of you have to know another meaning for cosh. Not Oshkosh bagosh, but so a billy club in England is called a cosh. So you can get beat with a cosh. Okay, and then you have tanh. Tanh of z is just the ratio of these two. So it's e to the z minus e to the minus z divided by e to the z plus e to the minus z equals, okay, what I'm going to do is I'm going to multiply top and bottom by e to the z. So I'm going to get e to the 2z minus 1 divided by e to the 2z plus 1. So that's tanh, cosh, and sinh. Okay? And because they're built on these exponentials, we can plug in any complex number we like, and they're totally well defined. Okay? Same thing for trigonometric functions. So you can have sine of z equals e to the iz minus e to the minus iz divided by 2I. And you have regular cosine of z equals e to the iz plus e to the minus iz divided by 2. Not 2I, just 2. Okay? So sine and cosine. Now, there's some interesting things here. If you plug in a real number for sine, it's a little weird that these sines and cosines have imaginary numbers in them in the formulation, right? But if you plug in a real number into z in either of these two expressions, then the imaginary parts of these cancel and the real parts stay together. And so these are real valued for real valued inputs. Okay? Normally, sine and cosine can only be between -1 and 1. That's not true for complex z. So you can have sine of, let's see, I have an example here. So you can have sine of 10i. Let's just try this. So sine of 10i is equal to, let's take the absolute value. This is equal to, so I'm going to plug 10i into iz and minus iz. And I'm going to get e to the minus 10 minus e to the plus 10 divided by 2. This is a huge number. This is bigger than 10,000. Right? E to the 10 is a really, really, really big number. So sine of 10i is huge. Okay, it has a really, really large radius. You can have sines and cosines that are much larger than plus or minus 1. And they're also going to be complex, right? Because there's probably an I in here. Okay, good. There's some really important identities I want you to know. And I'm probably going to put these on the first homework, so you will be able to work these out. So some identities are I times sine z equals sinh of iz. You'll have to work out the math, but it's not implausible that those would be related. Similarly, cos of z equals cosh of iz. And sine of iz equals I sinh of z. Cos iz equals cosh of z. I post all of my notes online, so you don't, strictly speaking, have to write all this down if you don't want. And then there's some really nice relationships to the function e. So e to the z equals cosh of z plus sinh of z. And it also equals cos of iz minus I sine of iz. So all of these functions are related. Hyperbolic functions, trigonometric functions, and the exponential function all intimately related. And I would encourage you to actually kind of figure out why all of these identities are true and really work it out, because it's really important to be comfortable with these different expressions for the things we're going to do later. Okay, there's a lot of solutions of partial differential equations that require you to be able to work with these types of functions and these types of functions for general complex variables, z. Okay, good. I have 15 minutes left, so that's just enough time to tell you about some weird things that can happen. So everything I've told you so far has been relatively straightforward. Okay, it's not too much of a stretch from what we know about real numbers to think about these things. But now we're going to start talking about some of the bad and strange things that can happen in the complex plane. So let's look at the complex logarithm. Okay, we're going to use the complex log a whole lot, and it's going to be really, really important, so this is kind of important. So we're going to define log as the inverse function of exponential, of e to the. Okay, so that's where we're going to start from, and we're going to figure out what are the properties of the logarithm if it is the inverse of the exponential function. So we're going to let z equal x plus iy, and we're going to let w equal u plus iv. And we're going to say w equals log of z. We're defining w to be the log of z. And we're going to define what this log function means. We're going to say that means that z equals e to the w. Right? This is what it means for log to be the inverse of the exponential function, is that if w equals log z, then z equals e to the w. Okay. Now, we're going to write this out kind of long ways. I'm going to start with this expression. So I'm going to say x plus iy is going to equal e to the u plus iv. Okay? Now, I can write that as e to the u times e to the iv. No problem. And I can also write that as e to the u, which is a real number, times cos v plus I sine v. Remember, both u and v are real numbers. W is the complex number. So these are all equivalent ways of writing x plus iy. And so based on this expression, I'm going to derive things that have to be true about u and v. Okay? So for example, x equals e to the u cosine v, and y equals e to the u sine v. Okay? And so what that tells me is that x squared plus y squared is equal to e to the 2u times cos squared plus sine squared, which is 1. And so what that tells me is that e to the u equals my radius, r. It equals square root of x squared plus y squared. Okay? Does that make sense? I'm just figuring out what has to be true about u and v if x plus iy equals this thing. One of those properties is that e to the u has to be equal to the length of z, the radius, the length of this z function, which means u equals the regular old real valued log of the length of z. Right? This is a real number. Length of z is a real number. Log of that is also a real number. Okay, now let's figure out what has to be true of v. So what has to be true of v? What is the function? What does the variable v look like in that expression? In this expression, what does v look like? Well, it looks a lot like an angle, right? E to the I v. It looks a lot like an angle. And so we have v equals theta, which is the angle of my function, my variable z. Right? Angle of z. So I have these two expressions. Now, what's interesting is that if I took this angle and I added 2 pi to it, I get the same angle, right? I could add 4 pi, 6 pi, 8 pi, it doesn't matter. And so it turns out that this v actually has multiple values that satisfy this expression. Okay, so the log, so what we're going to say is theta plus 2n pi also works. And so this entire big log function, log z, remember, log z equals u plus iv. So u is the log of the length of z plus I times v, which is theta plus 2 pi n, where n can be any integer. The set of all integers. Okay, so this is really, really strange. What this means is that our simple logarithm function that we've been using for years is much more complicated in the complex plane. So in the complex plane, our log function has a real part. This is u, which is just the log of the radius of my complex number. And it has an imaginary part, v, which is the phase angle of my complex number z, plus any multiple of 2 pi that you like. So what this means is that this is a multivalued function. Which is really strange. We're not used to that. Right? We're not used to our functions being multivalued necessarily. So this big Z, do you all know this symbol? It just means the set of all integers. It's from the German word Zahlen, which means numbers. Little epsilon here means n is an element of the integers. So I'm going to use this notation a lot. And we say for n equals 0, we have the principal value. Okay? So although there are infinitely many solutions to this log z, there's one special solution when n equals 0, and we call that the principal value. Okay, this is a little strange. So this function log is now slightly unsettling. There's something weird happening. And it's going to turn out to be really important later on that you can get these different multi-valued functions. So I'm just going to draw a picture to illustrate what's happening here before we end. Okay, so this is the W plane. This is the Z plane. And I have some variable Z, some complex number, which has an R and a theta. Okay? I have a complex number. And we can take the log of that complex number. And the real part, U, is equal to R. Okay? But the imaginary part, V, is equal to theta, or theta plus 2 pi, or theta minus 2 pi. These are all solutions to log of z. So if I took the exponential of any one of these points, I would get this exact z value. Okay? So that's what this long function formula means, is that the real part of my log is just log of the radius. This is log of r. And the imaginary part is just the angle of my complex variable z plus 2 pi, plus 4 pi, plus 6 pi, and so on. So we're going to use this basic idea that I can have multiple values to do things like look at the cubed roots of 1, all of the cubed roots of 1 in the complex plane. There's 3 of them. Or the cubed roots of -1 in the complex plane. So next lecture on Wednesday, we're going to get kind of a more concrete example of this type of behavior where you have multi-valued functions for something that's really simple and easy to understand, which is taking roots of the number 1. Okay, so this was a bit of the slow lecture. Next lecture, we're going to get into how to take the derivatives of complex valued functions when we can and cannot do it. The third lecture, we're going to be doing complex integrals, contour integrals, and path integrals. And then in the second week, we're going to be essentially learning to integrate all kinds of nasty functions that you would have never dreamt that you could integrate before. And they're all going to help us with PDEs and Fourier transforms and Laplace transforms. Okay, I'll see you on Wednesday.